Welcome back. This is the second part of lecture 13 on recurrent networks. We have already talked about how vanilla RNNs look like. So basically a set of very simple equations with three matrices mapping an input X to a hidden state H, the hidden state to an output Y hat, and another matrix that links the hidden state to the next time point. We have also seen that we can unroll the network, so or by running the network, unrolling the network in time or along a sequence, so that we use the same matrices that define this dynamic to produce outputs and hidden states. And we have seen that we can use this this feed-forward network, right? And train it like we are used to. We've seen that the gradient information is passed down in this computational graph from many different sources, and then needs to be added up, at the respective places. But we also saw that this means we need to have either a huge memory or are sufficiently satisfied with short sequences. But the sequence length isn't just limited by memory, by the memory footprint of those networks. We have severe problems with vanishing gradients. Exploding gradients are also a problem, but vanishing gradients are of much bigger concern. So why do we have vanishing gradients? Well, there's two reasons or two components in this network. One is this weight matrix used to map an input at time t and the previous hidden state at t-1 to the hidden state at time t. Propagating the gradient through these gates here, or through these activation functions, we have to multiply this by this matrix. And if the weights are small, sufficiently small, and the sequence length sufficiently long, we will multiply many small numbers on top of each other, resulting in a vanishing gradient. And also, if we have huge inputs to this 10H here, either positive or negative, these 10Hs will saturate. So the gradient, at those saturated places will become small as well. And then we'll multiply these guys on top of each other, even if the weights are okay. Yeah. So the idea now is, why don't we just skip these problematic components? By passing along, the untouched kind of inputs to the next time point. Well, you probably saw this when we looked at ResNets. The ResNet architecture is basically a sequence of blocks, ResNet blocks, and so an input X is added to this output of this block. So the block really needs to learn deviations from the identity mapping. And so this turned out to be very, very cool. And 20 years before, people have done this in this recurrent network, right? So we will look at how this works. There are two more ideas here, and they're not directly related to vanishing gradients, but they help also if the network to learn long-term dependencies. The first idea here is to introduce a so-called carrier or context vector, and we call this guy C. So that basically is similar to this hidden vector, but it will be used for passing untouched and unchanged, unscaled and unsquashed information to the next time point. And the third idea is also cool because we will organize the network such that it can learn what information to drop, coming in from the context vector, how much information to actually retain in the hidden state H, and how much of this information to pass, downstream to the next time point. And the underlying idea here is we will use gates, and that was Lewis's idea here. I have nothing to do with this. So obviously we will use gates that will define a scaling for each element within a given input vector. Let's say we have C coming in here and our usual input X coming in here. Now we will multiply X with this weight matrix W and push this through a sigmoid activation. So this is the logistic function between 0 and 1. Now G has as many components, as many elements as this vector C, and by multiplying both, we have a way of directly or individually scaling up or down all these components within C. Yeah, so this is like in the background here, you see those flood or this dam here. Although the input to this dam is all is constant for all those gates, you can think of having different kind of inputs, and then the scaling G here is an individual setting for each of these gates. How much of the water coming in should it let out? Yeah. Okay, so this is what the architecture looks like. Please don't panic here. We'll go through this step by step. Okay, so again, we have our context vector from the previous time point, ct minus 1, and the second hidden vector, ht minus 1. Of course, we have our inputs x, and this cell here, this element, representing one time point, produces also an output y hat of t. Now, the input x and ht minus 1 is concatenated and controls these three gates, right? So one gate is called forget gate, one is called the input gate, and one is called the output gate, and we'll look at exactly what these do and why they are called like that. But it's please note that all these gates come with their own weight matrices, yeah, and all are controlled by the input, which is the concatenation of x and the hidden vector of the previous time point. Now let's have a look first of all at what we already know. This part is the regular RNN way to compute a hidden vector. So the concatenated input is multiplied by a weight matrix with the corresponding dimension and maps into not H anymore. It's called a vector C tilde here. We will see later what it does. And think of this for now as really the hidden state. So this is what the network, maps all those new information xt into. Now, the gate ft, the forget gate now, controls how much old information, old context information is actually let into the cell. So again, this input vector, which is the concatenation of xt and ht minus 1, is multiplied by this weight matrix wf, pushed through the sigmoid activation function. By the way, we do have a bias term here too, a bias vector bf. And then, this vector g, right, like we had on the previous slide, scales each of these elements, okay? So values close to 0 block information coming from the previous time point. This will be added on top of something internal, right? And then is passed to the next, or is actually the, represents the actual context vector at time point t, and then is passed to the next time point. Now, the input gate does this. So again, our input is the concatenated vector made of x and h of the previous time point, and then it's multiplied by another weight matrix, wi, pushed through a sigmoid activation function, added a bias term, and now this defines how much of the hidden state, or this tilde context tilde vector, is actually mixed with the old context vector. Okay, so we have two gates here. One controls how much old information is passing through or is blocked, and how much recent information is let out or is let into this context vector. Yeah, or also how much recent information represented by C is let into this context vector. The third gate now is the output gate. So again, a weight matrix WO is multiplied by this input plus a bias term. This defines, again, a gating vector multiplied on this vector. Now, this is a little different from what we saw in the RNN case. The context vector is pushed through a second nonlinearity, a 10H nonlinearity, and now is gated into H. So actually, H of T is the real, let's say, hidden vector, okay? With the difference that we have two nonlinearities, and it's fed with historical information that is gated and actual information that is also gated, and this is something that we will pass down. Yeah, so we still keep C T, which contains this mixture of the actual information and the old information, but we also define how much of this is mixed with our hidden state. Okay, and this is a little more complex function. So the gradient update now, the gradient that is backpropagated from basically here can flow and at the actual time point t, at the last time point t, has to flow through here, but then can run on the Autobahn back to the very first input. Okay, and it will not be scaled and will not be squashed, and therefore it doesn't run into this problem of the vanishing gradient. The LSTM, of course, can be unrolled or unfolded. So we have our inputs and outputs for each of these time points, and this can be done. And like I said, the gradient can be propagated from the last to the first point along this Autobahn, only being pushed through additions and multiplications with no weight matrix and no squashing function. So a couple of years ago, 6 years ago, or 7 years ago, Cho et al. Proposed a new architecture called Gated Recurrent Unit, or GRU. And this architecture simplified a little bit the design of LSTM. So in GRUs, we only have one hidden state, so no carrier or no context vector. And we use only two gates, which basically define how much old information gets in and how much information is from within is mixed with the old information and gets out. So let's have a look At the equations real quick. We're not going to go into the deepest detail here, and I don't think this is really relevant for the final, so you might want to skip this, but for those who are interested. So the basic difference here is, like I said, there's just two gates. One is the reset gate. So what does it do? Well, we first concatenate our input vector xt with the old context, or the old hidden state c t minus 1. And so this gate, this reset gate, defines how much of this will be getting in, right? So this is again concatenated. So this gate defines how much old information will be coming into the calculation of the new context vector. And let's for now not look at this, but again, the concatenation here, right, defines this upper part of this input vector, which is the current x, and the lower part, which is this gated context vector, right? Okay, now we again, like in the LSTM, have this like temporary context vector c tilde of t. And again, this is gated with an update vector or update gate. Again, the concatenated vector xt and ct minus 1 is pushed into the sigmoid function. It's then defining how much of this context, of this hidden context vector c tilde, is actually then added onto the old context vector. Also, this is gated, yeah? And since we do not want this update vector to define how much of both the internal and the old is mixed, we define it as you know, the opposite, right? So the inverse. So at a position in which we define everything of the internal information has to be passed through, we want 0 of the same element of the old vector to be passed through. Okay. Okay. This for group. Now there are so many cool applications, and I've just collected a few here. And again, I invite you to collect more of these into the comments, or send us whatever emails. One of the coolest things I remember when I learned recurrent networks was this. So this is again Andre Karpathy's work. So you can also see this in a talk on recurrent networks here. So the problem statement is, given an image, generate text that is a description of the image. So image captioning. And so what is done in this work? Well, the image that is input here is represented by activations in a deep neural convnet, and this activation, this representation of the image, is then passed into a recurrent network that then, you know, conditioned on this image, generates text in, you know, in the way we have seen before, in a generative kind of way. So the output at time t is then put back into the network at t+1. And so you can see how this plays out. So man in black shirt is playing guitar, pretty accurate description. Construction worker in orange, safety vest is working on road. Perfect. Two young girls are playing with Lego toys. Well, almost. Girl in pink dress is jumping in air. So you see this already, and that was 2000, I don't know, 14, I think. Again, works pretty well. Yeah. Now, another example that kind of touches what kind of hidden information is stored and learned and retained throughout a sequence. This is an example of a paper by Ilya Sutskever, one of those famous machine learning guys, and he wrote in this paper, so this is just a huge LSTM, so they stacked 4 LSTMs and they have a 1,000-dimensional hidden state, and that by that time is just, as he states himself, minimum innovation and maximum performance. So but that's not what I wanted to say. So the cool thing here is that look at these 3 pairs of sentences or statements. Mary admires John, Mary is in love with John, and Mary respects John. And turning people around, John admires Mary, John is in love with Mary, and John respects Mary. So admiring, being in love with somebody or respecting someone kind of is mapped into this space here, and I'll come in a second to what is this space, because we have a 1,000-dimensional space, right? But in a way, the order of these relations is retained, although we have different people, so this is basically, I think it's a PCA, so a principal component analysis, something that we've learned already in one of those previous lectures. So projected on the 2 first principal components. And of course, to conclude this, I have to show you what we do in my lab with recurrent networks. So Ben, PhD student in my lab, trained a generative model, an RNN, to produce bee names, right? So we do have those markers that we glue on the back of bees, and for machines it's really easy to read those, but for humans it's really bad. And what we usually also do is to make sure that we are talking about the same animal. We combine the numeric ID with a name, and that is generated by this RNN. And by the way, it is kind of always a bee pun, right? Bee Marie, bee May, Bobby Ma. So there's some tricks involved that I won't go into detail here. And of course, there are so many different things that you can do with RNNs. For example, here, each of these agents sees its surrounding, and an RNN then defines the dynamics of its motion, right? So it tells this agent how to move. And this was done in Moritz's master thesis. He's also now a PhD student in my lab. Okay, let's summarize. First of all, recurrent networks are like a refreshingly different architecture from what we see, and they are designed to learn patterns along sequences, whether it be text or speech or time series. We can use these guys. We need to unfold or unroll those networks, because we can't train through loops. We have to resolve those loops, and this is done by unfolding and backpropagating the gradient through time. We've seen that the original formulation, the vanilla version, comes with feasibility problems. We can't train these guys for long sequences. LSTMs and GRUs kind of alleviate this problem. We still see that the length of the sequences that we can train LSTMs on is still limited to a couple of hundreds. But the gating mechanisms, and especially this context vector that the gradient can use as an autobahn, helps with the vanishing gradient problem. Good, that was it. That was lecture 13. There'll be 2 more, or maybe 3 more, I don't remember. I hope you still have energy and time to watch this, and hope you still enjoy it. Leave a comment and let us know how to improve this. See you all next Monday. Bye.